which is equal to here. So h nu naught plus Ke max is equal to half mv square. So half mv maximum square. So whenever the velocity is given, you have to use this equation. Suppose I get next one more equation here, h nu is equal to say h nu naught plus again E V naught. Stopping potential is given, so you have to use this equation. So h nu is equal to h nu naught plus E V naught. So where V naught is equal to stopping potential, and h nu is equal to energy of the incident light, h nu naught is equal to here the work function. Again, next one more equation here, h nu. So this is equal to hc by lambda is equal to hc by lambda naught plus ev naught. So whenever wavelength is given, you have to use this equation. So depends upon the question, depends upon the problem. So you have to prepare this all equations over here. But especially only one equation. So what is energy equation here? energy E is equal, what is that equation here? W naught plus Ka max. In the last class, I derived this equation here. So how this equation came over here? Simply here so whenever energy of the photon, so which is incident on the metal surface, what happens here? The total energy is used as two ways. So this one is equal to energy is equal to h nu. So this is energy of the photon. So one more technical name, this one is equal to photon. So which is incident on the metal surface only. So this energy is completely absorbed by these electrons only here. The energy is used as two ways. How many ways are there here? Two ways. So what is the first energy is equal here? Sum of the energy is used to. So remove the electrons from the metal surface only. So hence it is known as work function. The work function is equal to W naught. So that means here so what is the first way is equal here? Sum of the energy is used to. So to remove the electrons from the metal surface only. So hence it is known as work function only. So remaining energy is used to increasing the velocity of the photoelectrons. So that is nothing but kinetic energy only here, Ke max. So according to law of conservation of energy, what is that equation here? This energy E is equal to W naught plus Ke max. This equation over here. So in last class I told one example also, especially students' point of view. So which is example here? So whenever breakfast energy is completed here, energy of the students completed here, the energy taken at what time here? Maybe 8:30 to 9 time only here. The total energy given to the students is used as two ways here. Some of the energy is used to listen the classes, or to do study hours also here. Some of the energy. So remaining energy is used to extra activities here. So what are the extra activities here? Extra activities nothing but to seeing the mobiles, YouTube, or again next one again games, again or PUBG games, anything also here. That is extra activities only here. The different persons having a different percentage only here. So this one is equal to maybe 95%, this is equal to 5%. So 95% of the total energy is used to listen to the classes only here. Like remaining energy only 5% to extra activities. Okay, they will success also here. They will get medical seat only here. Suppose like this one is equal to 90% also maybe no problem only here. Up to going on, this one is equal again 5%. This is equal here the 95% only here. What happens here? Already you know this situation here. That means here the total energy is given to the students. So which is used to 5% to only listen to the classes only here. So remaining 95% to do extra activities only here. They will not get medical seat only here. Okay, since this depends on this percentage more. Same this also here the total energy is used as two ways. How many ways are there? Two ways. Some of the energy is used to remove the electrons from the metal surface only. So hence it is known as work function. And again second one again remaining energy is used to again we can increasing the electrons of velocity electrons only here. So hence what is that equation here? E is equal to W naught plus Ke max. So E is equal to W naught plus Ke max, okay? And again, next one I told here what are the laws of the photoelectric effect here. I explained this laws of the photoelectric effect from the Einstein photoelectric equation. So how many laws are there here? 4 laws I explained, okay? Again, next one, applications. So applications. So applications of Einstein's photoelectric equation. Einstein's photoelectric equation. So first application here. So what about kinetic energy? Maximum kinetic energy of the photoelectrons is equal here. So first point here. So maximum kinetic energy of so photoelectrons is. So what is that equation here? Same this equation only here. So E is equal to W naught. So E is equal to W naught plus Ke max. So what is the Ke max is equal here? So Ke max is equal here the E minus W naught. So this is one of the main equation here. So how can you find out maximum kinetic energy of the photoelectrons is equal here. So Ke max is equal to E minus W naught. Suppose in this question here, the energy is given in terms of the frequency only. And what is the equation here? E is equal to h nu. And again next one, W naught is equal to h nu naught. So whenever frequency is given, the frequency of incident light is given and threshold frequency is given here. Threshold frequency is given. So you have to use this equation. The kinetic energy of the maximum is equal to so h nu minus h nu naught. So this is equal to one equation here. Suppose frequency value is not given here. Again the incident wavelength is given. So what is that equation here? Ke max is equal to so h nu. So what is the nu is equal to what is that equation? Hc by lambda. So already I told this one here. We did some solution last class one here. So hc by lambda minus h nu naught is equal to hc by lambda naught. So this is equal to one equation here. The maximum kinetic energy of the emitted photoelectrons is equal to hc by lambda minus hc by lambda naught. So whenever wavelength is given here, you have to use this equation. So whenever this frequency is given, you have to use this equation. Or simply here the energy is given, you have to use this equation. So this is equal to first application. Okay. Again next one, the first application. One more equation here. Again next one. First application, this is equal first point. Again, next one, second point. In the first application, second point. So what is the maximum velocity of the emitted photoelectrons is? Note the second point here. Maximum velocity of. So photoelectron is simply PE means photoelectron. We have to write complete name only here. So the maximum velocity of the photoelectron is. So you have to use any equation, Ke max is first equation, Ke max second equation, third equation, any equation here. So depends upon the question only here. So what is the kinetic energy equation? This is equals half mv square. So why you are using this equation instead of EV naught here? Since asking the question is equal to here what is the maximum velocity of the emitted photoelectrons only. So maximum velocity emitted photoelectrons. Now what is the equation here? So Ke max is equal to half mv maximum square. So half mv maximum square. So which is equal to any one equation. Just highlight this equation here. So h nu minus h nu naught. Okay. So what is the V max square equation here? V maximum square is equal, this is equal here. So H is equal to common also here. This is equal into by 2 means into 2. So into 2H by M. So into nu minus nu naught. I wrote direct equation here. So V maximum square is equal to V maximum square is equal to H is equal to common here. So this is equal to H by. Again this is 1 by 2 means into 2 1 here by M. 2H by M into nu minus nu naught. So what is the V max is equal, what is that equation here? This is equal to root of. So 2H by M into nu minus nu naught. So in terms of wavelength, in terms of frequency only here, the maximum velocity of photoelectrons is, the maximum velocity of the photoelectrons is Vmax is equal to, so root of 2h by m into nu minus nu naught. This is equal to one equation. Again, next one. Or, so one more equation here, V maximum is equal to, in terms of the frequency is completed, okay? Now in terms of the wavelength, I will let direct equation, you have to use this formula only here, Hc is equal to common here. Same this equation here, so this is equal to, Hc is a common here, 2Hc, so by m, 2Hc by m. So into remaining equation is equal to here, so 1 by lambda minus 1 by lambda naught. So this is the maximum velocity of the photoelectrons in terms of the wavelength. So whenever the wavelength is given, you have to find out again maximum velocity means you have to use direct this equation. This is equal first application, second point, okay? So what is the first point here? Energy maximum of electrons. Second one is equal here, so the maximum velocity of the photoelectrons. Okay, next second application. Second application, second application. Suppose this nu1 and nu2 are the frequencies of incident light. First frequency of light is equal to nu1 and second light frequency is equal to nu2. So this one is equal here the first one, again this is equal to second one. Two lights. So two lights of frequencies nu1 and nu2 are incident on the same cathode surface. So same cathode surface means here, so already we know this experiment also, just one simple diagram here. So one is equal to here the cathode, this one is equal to anode one here. So this is equal to here the one quartz window, this is equal to one transparent window. Suppose here this frequency of light is equal to say nu1, so which is incident on this cathode surface, first case. Okay, again second case here, same cathode again surface here, same emitted surface only here, this is equal to same, this is equal to A1 here, so this is equal to transparent window. This frequency of light is equal, this one is equal to say nu2. Here condition here, the emitted surface C should be remains same only here, So what we have to change is equal here, first frequency is equal to nu1, second frequency is equal to nu2. So frequency is nothing but what happens here, we have to change the so different colors of the lights only here. How can you send means by using this filters also, okay, already I told in the experiment also, okay now. So first one, suppose this is equal blue light sending over here, the frequency is equal to nu1. Second one is equal to maybe red light or violet, anyone also here. So now in this case here, what is the ratio of maximum kinetic energy? So two waves of, so two light waves of frequencies nu1 and nu2. Two light waves of frequencies nu1 and nu2 are incident. I will continuation only here. So incident on the same cathode surface, same metal surface, okay, same cathode surface. Then the ratio of maximum kinetic energy, simply Kmax, no need of maximum kinetic is long, no need here, simply Kmax. The ratio of kinetic energy maximum Ke max of this two light, this Ke max of photoelectrons is given by, just imagine what is the equation here. So what is the condition here? The two light waves or two lights, anyone, our frequencies are given is equals to nu1 and nu2. Same this one here. This first again, this light frequency is equals to nu1. So which is only what happens here? This electrons are ejected only here, electrons are ejected only. Second one, the same cathode surface, same experiment here, but we have to change only, the frequency of the light one here. So now this frequency is equals to nu2. So first one, this one is equals to maybe blue color, okay, like this one is equals to maybe red color, okay. That means here the change in the colors one here. So whenever change in the colors means what happens here, frequency also changes one here. So now again here, what is the ratio of the maximum kinetic energy of the photoelectrons is? Okay, so what is the Ke max equation here? Same, now you have to use this equations here. So Ke max is equals to E is equals to W naught, okay. So Ke max is equal to, first one E is equal to here, the E is equal to W naught plus Ke max. So what is the Ke max equation here? So Ke max is equal to, so E minus W naught. Ke max is equal to here, so E minus W naught. So now tell me here, in this application or maybe in this question, maybe in this problem here, so which values are given here? Frequency or wavelength here? So frequency given on here. So frequency given on here. Now what is the equation here? So E is equal to H nu, again W naught is equal to H nu naught. Depends upon the application. So depends upon the question, you have to write this equations only. Okay. So this is equal to Ke max. And now what is the equation? H is equal to common. Otherwise, again, this is H nu minus H nu naught, okay? Suppose in case of the first light, what is that equation here? First light. So Ke maximum 1, so which is equal to H nu 1 minus nu naught. Okay? So in case of the second light is equal to here, Ke max 2 is equal to here. So Ke max 2 is equal to here. So H nu 2 minus H nu naught. So first light of frequency is equal to nu1. So now what is that equation here? Ke max 1 is equal to H nu 1 minus H nu naught. Okay, next one. Second light of frequency is equal to Ke max 2. What is that equation here? H nu 2 minus H nu naught. Okay. But again, you have to find out, you have to calculate what is the ratio of kinetic energy maximum of this photoelectrons is. So what is that equation here? So this is equal to equation 1. This is equal to equation 1. Equation 2. So now dividing these two equations here, equation 1 by equation 2, which implies, so what is that equation here? So Ke maximum 1 by Ke maximum 2 is equal to here. So this is equal to here the H nu 1 minus H nu naught by H nu 2 minus H nu naught. Any simplification here? Just think about this one here. So in the numerator, denominator here, H should remain constant one here, and also cancel also here. What is that equation here? So this is equal to nu 1 minus nu naught by nu 2 minus nu naught. So this one is equal to say Ke maximum 1 by. So Ke maximum 2 is equal to here. So nu 1 minus nu naught by, so nu 2 minus nu naught. If you know this application here, you will get the answer of this type of application within 1 second or 2 seconds only. If you don't know application, what happens, it will take some time also. So this is equal to second application. What is second application here? Whenever the frequency of the light wave changes only here. So first light frequency is equal to nu 1, second light frequency is equal to nu 2. Then what is the ratio of Ke max of the photoelectrons is given by. So what is that equation here? So Ke max 1 by Ke max 2 is equal to Ke max 1 by Ke max 2 is equal here. So nu 1 minus nu naught by nu 2 minus nu naught. Okay. So this is the frequencies only. Okay. So whenever you have to explain the frequencies here, so tell me same as again this wavelength also. That also compulsory one here. Okay, now again third application. Third application, if the two light waves of wavelength, so not frequency, is a wavelength. This one is called a wavelength. So wavelength. I am rubbing off the second application, writing continuation third one. But don't do like to me here. You have to write third application, you have to write this again next time also. Okay? So wavelength. So one is equal to lambda 1 and lambda 2. So this is equal to lambda 1 and lambda 2. Are incident on the same cathode surface, then the ratio of Ke maximum of photoelectrons is given by. So one is equal here, this wavelength of frequency, one is equal to lambda 1, and again second one is equal to lambda 2, lambda 1 and lambda 2. Lambda 1 and lambda 2. Just imagine what about the equation is equal here. So I told this Ke max in terms of wavelength also, okay? So what is application here? Two light waves of wavelength. So first light wavelength is equal to lambda 1 and second is equal to lambda 2, okay? So all incident on the same cathode surface. Then the ratio of Ke maximum of the photoelectrons is given by. Same equations on here. So E is equal to W naught plus Ke max. W naught plus Ke max. So our Ke max equation here, E minus W naught. So I will direct equation here. So this is equal to Ke max is equal to H nu minus H nu naught. I direct this equation here. This is equal to here the Hc by lambda minus Hc by lambda naught. So Ke max is equal to Hc by lambda minus Hc by lambda naught. So in this equation Hc also common here. Hc is equal to common. So this one is equal to Hc is a common here. So 1 by lambda minus 1 by lambda naught. Okay, first light. This wavelength is equal to lambda 1. So what is that equation here? Ke maximum 1 is equal to Ke maximum 1 is equal to here. So this is equal to Hc into, so 1 by lambda 1 minus 1 by lambda naught. So this is equal to equation 1. Second one is equal for second light. This Ke maximum 2 is equal to Ke maximum 2 is equal to here. Hc into. So 1 by lambda 2 minus 1 by lambda naught. Clear this one? Same, instead of the frequencies, you have to use the wavelength one here. So Ke maximum 1 is equal to Hc into 1 by lambda 1 minus 1 by lambda 2. Again, Ke maximum 2, what is that equation? Hc into 1 by lambda 2 minus 1 by lambda naught. So now dividing these two equations here. So equation 1 by equation 2 is equal to Ke maximum 1 by Ke maximum 2 is equal here. So let direct equation here, Hc and Hc is cancelled here. So this is equal to 1 by lambda 1 minus 1 by lambda naught. Again by 1 by lambda 2 minus 1 by lambda naught. Note these equations. So this is the ratio of the maximum kinetic energy of photoelectrons when different wavelength of the light is incident on the same cathode surface. So this is the third application here, But don't by heart any applications here. You have to practice just concept orientation only, concept orientation. Whenever if you know this all applications here, the sums very simple and very easy also. So don't do the sums without these applications. Again, lengthy also again difficult only. Again, next fourth application. Fourth application. In the previous application, we changes only lambda 1 to lambda 2 on here. We found that the ratio of the maximum kinetic energy is on here. Suppose in this application here, the kinetic energy also changes from K1 to K2. So then what is that equation here? Suppose two light waves of wavelength is equal to lambda 1 and lambda 2. This wavelength changes from lambda 1 to lambda 2. Again, then the kinetic energy changes from K1 to K2. Then what is the work function W naught is equal to say how much? Work function W naught is equal to how much? If this is the fourth application here, so wavelength of incident light, you have to complete also a very simple light, okay? Wavelength of light. So wavelength of light changes from lambda 1 to lambda 2. The wavelength of light changes from lambda 1 to lambda 2. Then kinetic energy of photoelectrons changes from K1 to K2, Wavelength of the light changes from lambda 1 to lambda 2, and then kinetic energy of the emitted photoelectrons changes from K1 to K2. Then the work function simply W naught. W naught means a work function. This also I am writing here, work function, simply Fn, work function. So is given by, this is the previous question also here. Previous question, AFM question. The two light waves changes, wavelengths of two light changes from lambda 1 to lambda 2. Then kinetic energy of the photoelectrons changes from K1 to K2. Then what is the work function is equal here? What is the equation here? The energy is equal here. So energy is equal to so W naught plus Ke maximum. So now you have to think about here. So what is the E is equal, what is the value here? And W naught is equal, what is the value here? Ke max is equal how much here? See this application here. So wavelength of the light, incident light wavelength is given. So incident light wavelength is given means what happens? E is equal to hc by lambda. So this one hc by lambda. And now we have to find out W naught. So same this value here, this is equal to W naught. And a kinetic energy maximum, this one is equal to K. K means here the kinetic energy maximum. So this is equal here the main equation. Okay now? So now again here the first light. Okay, first light. So what is that equation? Hc by lambda 1 is equal to say, so W naught plus K1. So this is equal to first equation here. Okay, next one. Second one is equal to. So hc by lambda 2 is equal to here. So W naught plus K2. Since here the wavelength of the light changes from lambda 1 to lambda 2, again here the kinetic energy changes from K1 to K2 only here, K1 to K2. So now what is the W naught is equal, what is that equation? So this one is equals equation 1, this is equals equation 2. So now just 1 second you have to think about this equation. How can you find out W naught is equal here? Dividing these two equations, or again equation 1 minus equation 2 only here. Just 1 second think about this. Suppose here the equation 1 minus equation 2 means what happens here? So this equation 1 minus equation W naught, again this is a minus W cancel on here. Okay, it is not possible, lengthy also, okay now? Okay, again dividing these two equations over here. So equation 1 by equation 2 is equal here. So now again equation 1 by equation 2 is equal to. So equation 1 by equation 2, which implies what? Equation 1 is equal to hc by lambda 1 by hc by lambda 2 is equal to here. So what is that equation here? W naught plus K1 by again W naught plus K2. Clear? So now again HC and HC is cancelled here. HC by lambda 1. Again by HC by lambda 2, what happens? HC is cancelled here. So what is that equation here? So lambda 2 by lambda 1 is equal to, so W naught plus K1 by, so W naught plus K2. Now simple equation over here. So in this equation W1, again lambda 1, lambda 2, K1, K2. You have to find a W naught equation, simple equation. Now you have to do the remaining equations also. So now again you have to do cross multiplication. What is that equation here? So lambda 2 into this value. I will have direct equation lambda 2 into W naught, again plus lambda 2 into K2, So which is equal lambda 1 into this value here. So lambda 1 into W naught plus lambda 1 into K1, So now we have to write here, this W naught terms of one side here, this one one side here. It will go to this side, this becomes again negative value here, again this one, again this is equal, again right side over here. So what is that equation here? So lambda 2 W naught, so minus again W1 into lambda naught. So which is equal lambda 1 K1 minus lambda 2 K2. In this case W naught is equal to common also here. So directly W naught is equal to here so lambda 1 K1 minus lambda 2 K2 by, so lambda 2 minus lambda 1. This is one of the most important equation. One time directly given this equation only here. Again 2 times given based on this formula also here. Wavelength changes here, again K1, K2 changes one here. So what is the work function is equal to how much one here? If you know this application here, the sum is very simple and easy also. Okay, so this one is the fourth application. Now again. Already I told one application equation also here. Same. What is the relation between the stopping potential and frequency is equal here. What is the graph is equal here? So this is the one straight line like this one. Okay. So now extending this line. So this point is equal to O, this is equal to A, this one is equal to B. Okay, already I told this equation in last class also here, very important equation. So maybe this is equal to fifth application or again the same this equation continuation also here. Okay. In this case here, what is the slope? What is slope of the graph is equal to how much here? So what slope is equal to how much here? This slope is equal, this one is equal to H by E. So how this slope value is equal here? Same this equation over here. H nu is equal to say H nu naught plus EV naught. So once again I will write this equation is also here. Again please note on fifth application. This frequency value is taken on x-axis here, and again next one stopping potential on y-axis. Again don't get doubt also here. What is stopping potential also here? I told so many times also here. So what stopping potential, what happens here? Whenever here the negative potential again increase here, what happens here? The negative potential of the anode increases here. At a particular negative potential here, the photoelectric current becomes to zero only. Hence, that potential is known as stopping potential or retarding potential. Okay, this one. Okay, already I told this one here. Okay, what is the graph is equal here? What a graph is equal here? So H nu is equal to H nu naught plus EV naught. So what is EV naught equation here? So EV naught is equal to H nu minus H nu naught. So what is the V naught? What is that equation here? HU by E into nu minus HU by E into nu naught. In the last class also given this equation, am I right or not? So this V naught is equal to HU by E into nu minus HU by E into nu naught. Same this equation is equal to y is equal to mx minus a. Y is equal to mx minus a. So instead of y, this one is equal to V naught. The negative potential, the stopping potential on y-axis over here. And remaining again next, this is equal, x is equal to new frequency, okay? Again next one, slope is equal to how much? HU by E. So this is equal to graph. So this is equal to here, the slope is equal to HU by E. Slope is equal to HU by E. So slope is equal, this is equal to theta on here. So tan theta is equal to HU by E. Again next one. Again HU by E into nu naught. This is equal to O, this point is equal to A, this point is equal to B. So OB is known as y-intercept, y-intercept. So what is the y-intercept is equal to how much here? Y-intercept is how much value? This is equal to here the, so H nu naught by E or W naught by E only. Directly work function is given here. So find out the y-intercept means what is the value is equal to here? So W naught by E only. Again next one. Again what is OA is equal to how much? This is equal to again nu naught. So how this equation, this value came so here. In the last class I told this equation also here, okay? So this threshold frequency is equal to here. So OA is equal to x-intercept here. That is the threshold frequency. The threshold frequency is equal to nu naught. The x-intercept is equal to threshold frequency, that is equal to nu naught, okay? Compulsory one question based on this formula also here. So in this case here the slope is equal, first point slope is equal to HU by E. So this is equal to HU by E slope. First one is equal to slope. The slope is equal to tan theta is equal to M, which value is equal to HU by E. Second one is equal to here, x-intercept is equal to OA. So OA is equal to nu naught. So where nu naught is equal to here the threshold frequency. Again third point is equal, this is equal to OB. So OB is equal to here the y-intercept here. So this one is H nu naught by E, or this is equal to W naught by E. So W naught by E. Enough of these applications here. So now I am going to explain some problems based on these applications and these equations. Completed. Okay, next, first sum. Please note down. Find the work function. Find the work function of a metal find the work function of a metal with the energy of incident photon 7.4 electron volt. Compulsory you have to observe these units also here. Energy units is equal, one is equal joule or electron volt here. So don't get confused also here. So whenever electron volt is given, a very simple solution also here. So 7.4 electron volt and stopping potential 4 volts. Stopping potential 4 volts. Just first again think about this question and again solution also here. Find the work function of the metal with energy of incident photon. Incident energy is given here. This is equal to 7.4 electron volt. And the stopping potential is equal to 4 volts. So what is the work function is equal here? First one basic equation E is equal to what is that equation here? W naught plus Ke max. Now I can think about this equation here. In this question, which values are given here? So directly here the energy is given over here. Clear? So energy is equal to how much? E is equal to 7.4 electron volt. Okay, next one. So Ke max is not given sir here, but again W naught is given. So what is Ke max? What is that equation here? So Ke max is equal to this one is equal to E V naught. E V naught only here. So this kinetic energy maximum is equal to E V naught. So why you are using this equation? Ke max is equal to half mv square there is here. But in this question what happens here? Stopping potential is given over here. Stopping potential is equal to how much? Well, this is equal to here. The V naught is given here. So V naught is equal to how much is given here? So 4 volts. So this is equal to again E into 4 volts. So this value is equal to 4 electron volt. So now we have to check out this equation here. Energy is equal to 7.4 electron volt. Again, Ke max is equal to 4 electron volt. So both the units verified over here. So hence what is that equation here? So E equals 7.4 electron volt is equal to, so W naught, you have to find out W naught value, and again Ke max is equal to 4 electron volt. Simple logic. So W naught is equal to what is the value here? 7.4. Again minus 4. So this is equal to 3.4 electron volt. You have to check that options here. Suppose electron volt is given here. Enough this answer here. 3.4 electron volt. Suppose electron volt is not given, so here joules is given here. So how can you do that question here? This is 3.4 into, so joules. 1 electron volt is equal to 1.6 into 10 power minus 19 joules. Okay. Yes, please note this value here. So W naught is equal to 3.4 electron volt. Next, second question. Second question. Second one. In a photoelectric experiment, the wavelength, or simply WL means wavelength, the wavelength of light incident on a metal is changed from 300 nm. Allow nm means nanometers only, nanometers, not meters here, not centimeters here, not angstrom unit also, nanometers only here. So now we have to convert into meters. Maybe we have to convert it to angstroms. Okay. So 300 nanometers to 400 nanometers. 4 nanometers. Then find decrease in stopping potential. Decrease in stopping potential. Decrease in stopping potential. Today how to do this homework question? Just I will give hint only. In the photoelectric experiment, the wavelength of the light incident on the metal is changed from 300 nanometer to 400 nanometers, okay? So you have to convert this value into angstroms only. Angstroms, okay? So how can you convert means what happens here? So this is equal to nano is 10 to the power of minus 9. Clear that? 1 nanometers is equal here. So 1 nanometers is equal to 10 to the power of minus 9 meters. Okay? Again, angstroms, what is the equation here? So 1 angstrom unit is equal to 10 to the power of minus 10 meters over here. So that means here the 300 nanometers is equal to 3000 angstroms on here. Clear this one here? So directly how to convert into angstroms one here. So why angstroms means here, directly what is that equation here? So energy is equal to hc by lambda one here. Hc is equal to 12,400. So lambda must be in angstroms one here. Okay? So first you have to convert into angstroms here, 3000 angstrom to 4000 angstroms. Then the decrease in stopping potential is equal here. So what is that equation? Decrease in stopping potential is equal to here. The energy E is equal to W naught plus kinetic energy maximum. In this question here, this incident light changes from lambda changes one here. So what is the equation is applicable here? So hc by lambda. Clear? So which is equal again lambda naught. Okay, max is this one is equal to EV naught. So again, first point is hc by lambda 1 is equal to W naught. Again, plus EV naught is equal to EV1. So this is equal to here equation 1. Second one is equal again here so hc by lambda 2 is equal to W naught plus EV2. So these are the equations one here. Already we did some applications also this type of sums. Okay. So now again here this wavelength changes lambda 1 to lambda 2 one here. So again now again here the W naught value is not given here. So only what is V1 minus V2 is equal how much here? This question is given 2019 mains question here. 19 mains question. So now how can I do this means here so we don't want W naught here. We don't want W naught, what happens here? So now again equation 1 minus equation 2 or equation 2 minus equation 1. But in this question here decreasing stopping potential one here. So initial stopping potential is equal to V1. Second one is equal to V2. So what decreasing stopping potential, what happens V1 minus V naught one here? So now equation 1 minus equation 2 which implies here. So equation 1 so minus equation 2 which implies. So directly this is equal to hc is a common here. So 1 by lambda 1 minus 1 by lambda 2 is equal to W naught is cancelled here. So which is equal to E into V1 minus V2. Shall you do the remaining calculation here? So hc is equal, this value is equal here to the 12,400 when lambda must be angstroms. Okay. So this one is equal to 12,400. Again. So 1 by lambda 1 is equal, this one is equal to 300 nanometers here. So lambda 1 is equal, lambda 1 is 300 nanometers here. So which value is equal to 3000 angstroms. You have to convert to angstroms. So lambda 2 is equal, what is the value here? So 400 nanometers here, which value is equal to here so 4000 angstroms. So this one is equal to 12,400 into 1 by lambda 1. Lambda 1 is equal here 3000. So minus 1 by lambda 2 is equal to 4000. So which is equal here the E into so V1 minus V2. Okay. And E is equal to same V1 since this answer will come in electron volt one here. So no need of 1.6 that value here. This answer will become electron volt. Shall you do this remaining calculation here? So this one is equal to 12,400. Again by 1, 2, 3 just common one here. 1000 is a common here. So 1 by 3 minus 1 by 4. So this one is equal to E into V1 minus V2. We have to find out E into V1 minus V2. Yes, to do this question. I will stop here. So remaining sums we will explain tomorrow also. Find out E into V1 minus V2. E into V1